Hi guys, can you give me a sound check?
I can hear you.
Thank you.
I can hear you too.
Yeah, we can hear.
I am struggling today. What the heck am I doing? Just give me 1 second, guys. I gotta log in for my iPad. Okay. All right, guys. So today I'm just gonna start with like some of this. This isn't strictly speaking part of the class, but just throwing some of the stuff that I think is important for your long-term career development out there. And one of the important things that I did get started doing fairly early, surprisingly. I don't know why, about when I was kind of your age, my senior class, I started reading technical papers. Okay, so every field, every business, every technical field, every technical area has its own technical journals. Okay, and so for chip design, the most important technical journal is this IEEE Journal of Solid State Circuits. Okay, now if you were going to work on, I don't know, power circuits or robotics or designing processors or doing programming. Like there's I'm not a programmer, but there's like IEEE Computer is a journal that's for, sort of the main software thing I'm familiar with. Okay, so this is the solid state. And so what's important is, as you guys, what you're learning right now is really the basics of like making you guys sort of like a white belt. You guys are just sort of learning to crawl now, getting a taste of everything in college. Then when you go get a job, you're going to do a lot of your learning on the job, which is what people do. But that's not enough, because what happens is when you go to a job, almost by definition, unless you're in a program that's pretty rare these days where they're moving you between different departments, etc., you start working on a pretty specific area. And how should I put it? Engineering is kind of like, it's a science, but it's also a craft. And so what you're learning on the job is very, very important. Don't get me wrong, it's like 99% of your learning. But you're learning that sort of the orthodoxy of that particular place you're working at. You're learning how the people in that particular place are doing the work they're doing in the year 2020, okay, with the technology that they're working on, so on and so forth. But that's the most important thing you do as a beginning engineer working, as a beginning professional. But as you progress through your career, you need to keep track of what's happening outside your immediate group, design group, your immediate test group, whatever it is you're working on, your immediate company. You have to start looking at what's happening around you, what's on the bleeding edge, what's coming in 4 or 5 years, what's the the most bleeding edge guys are doing in the field. Now you get an inkling of that through things like, I don't know if you guys read, these are really good sources like Wired website, Wired, like Recode, EE Times. These are all nice journals for, or I'm sure you guys, I don't know where else you get your news from, your sort of your technical news. You hear that so and so has released a new chip or whatever. They're really good, but they're at a very shallow level of technical information. So to get to a very deep level of technical information on new stuff, you have to go to these sources. And again, for chip design, it's the IEEE Journal of Solid State Circuits. So given that, I again figured that you guys, hopefully, they're not hopefully, but maybe there's some gamers or something in the audience today, or your guys are otherwise familiar with NVIDIA. I pulled one of their papers that's from, was it from 90, from, is it 19 or 18? I forgot where this is. This is recent. So this is from 2019. Okay, November 2, 2019. And meaning that this was work that was done at an NVIDIA R&D center. Probably the work started in 2017. They got their chip back in like around sometime in 2018. By the time they did design, all that stuff, and got it fabricated and characterized it. Sorry about the dog, guys. And they submitted the results sometime in early 2019, okay, for it to get published. So the first thing to notice from this is work that was done, even if you're reading it in late 2019, this was work that was done 2 or 3 years ago, just the way it is in our field. By the time you get everything done, submit the paper, some bit of time has gone by. It's not what NVIDIA has, is releasing in a product now. This is what they had 2 years ago, say. Okay, so that's one. Two, this is a good source for, about who is doing, specifically who is doing work. So, the heck. So, here's a really important section, is the author list. Okay, so this starts, because it's any field is a collection of people. You start realizing that. And as you get more and more senior in your field, it's important for you guys to become, known experts outside your company. And so these are people like that. And that, this is one of the ways you do get known outside your company, by publishing technical papers, etc. Here, this guy, Brian Zimmer, is the main author. And, he's got a list of collaborators. And one thing you can do, for example, is, this is something we did last semester, but I'm still struggling with doing something a little bit different. But you can go, sort of look up Brian Zimmer on LinkedIn, for example, and see what he's up to. If you're interested in the work he's doing in this paper, let's say you want to go work on this area or find out more, this is an indication of who at NVIDIA is working on this particular thing. And so that's sort of one really good areas. And then you can figure out what other papers Brian is published. If he's published this, might be other things in this area if you're interested in finding out more about this area that he would have done under his name. Okay, so these are the different, and then, whoops, sorry, the different parts of this paper, you know, so you got the title, okay, great. It's already telling you something about what they're doing. Got the list of authors, and here's the one of the most important sections is the abstract, which is a brief description of what these guys are doing and why. So, by the way, this is, I don't know if I mentioned this to you guys, but my wife is just started her PhD in USC, I think about a year ago or something like that, a year and a half. And one of the things she had to learn the hard way is you want to look through a lot of these technical papers. So, but you don't want to read these word for word until you're sure it's something you're really interested in. Okay, you want to sort of peruse this paper. You want to spend maybe 30 minutes on this paper, because if you really dig into this paper, it might take you, even for somebody like I'm a professional in this field, understand what they're talking about to a big extent. It might take me a whole half a day, 4, 5, 6 hours to maybe longer to go through this paper in all its detail, okay, and why they're doing, what the equations mean, what they've really accomplished, etc. But I can peruse this like in about 30 minutes. And the first thing I do is I look at the abstract. They're telling you the highlights of what they've done. They're telling you what the figures of merit are. Here they're talking about this is for a deep neural net accelerator type of problem. It's talking about it's using a mesh network with multi-chip modules. So it's building up big and small circuits. It's allowing you to do a scalable design. It's talking about the process it's in, 16 nanometer process. It's giving some figures of merit, and sort of just telling you what the main things are here. So that's the first place to go. Okay. The second place I go is I jump all the way out to the end. Okay. I start usually look at the experimental results and sort of the conclusions and the measurements here. This is sort of where you get the bottom line of what this thing actually did. They're giving you a table here of how their work is different from what came before. They're showing the different process technologies that other works had. That's important because if you're giving a power consumption number or area number, and you're in a 16 nanometer process, you want to make sure you're fairly, you're not going to look as good as somebody that did exactly the same thing in an 8 nanometer process. So I want to call that out and make sure that the reader understands that. Okay, and then it's got a bunch of measurements, etc., out here. And then if you are interested, so the next place I look at is I look around and see if there's particular areas I'm interested in this paper. So I know generally what they're doing. I personally like sort of high-speed communication. And so I would go out to how they did their multi-chip module layout. And, they talk about the specifics of trace sizes, etc., how they routed that. They talk about how they the communication protocol they used, the sort of the layout of the basic chip. So I might, if I'm interested in this area, I might start digging into these details and find out more about how they did this. If I'm even more, maybe I'm interested in the way the data is moving around. Okay, so I look at, I'd be looking at this section. And then if I'm really working, or this section, and if I'm really working on this field or very interested in it, I would go read this thing from the beginning to end. But say for every paper you might read from beginning to end, you might just skim through, 20, just sort of like what's happening, and you want to kind of get the gist of what's going on. So I can't say how important this is, especially starting year maybe 3 or 4 of your work. You don't want to be in a situation where you're stagnating and just doing the same thing over and over again and not increasing your knowledge growth. Whether you're bringing that type of information back to the company you're working at or back to the organization you're working at, and helping enhancing your work there and helping the organization there, or whether you want to move to another company and you want to sort of build up your knowledge base, so you're more valuable. But it's important for both of those. Okay, any questions about that, guys? Again, this isn't something you have to do for the class or anything like that. It's just something I wanted to share with you guys. That's very, very important. You see, year 10, year 15 of somebody's work. Unfortunately, a lot of engineers are kind of like in a stagnant place, that they're not increasing their knowledge base. And this is really, one of the primary ways you can increase your knowledge base fast. Okay, let's see. Where am I? Slide deck. Sorry, guys, I'm having all sorts of computer problems today, so let's try this again. Okay, cool. Okay, so today we're going to talk about the processing of how do we build these silicon wafers. Okay, so you guys remember that they make these chips in these semiconductor wafers that are, it's like a wafer. It's about, most wafers you see in high-end processes are 12-inch wafers now, okay, or 300 millimeters diameter. And it's about 1 millimeter thick, okay, or very specifically, usually 750 micrometers. Okay, so if I look at this from the top down, you see this wafer from the top, it's 12 inches in diameter. If I look at it from the cross section, from the side, and cut across, I see something like this drawing here. Okay, so this represents the so-called substrate, okay, which is this silicon. This is really kind of something, so let's say that if this was 1 millimeter thick, the substrate goes the whole thickness, but all the sort of the interesting stuff that happens in the top, say, 3 to 5, maybe to 10 micrometer of silicon. So imagine this is like really thick, it's going down there, And this is the very top of this area here is the very top of the silicon wafer. And so here, so we're going to go into this in detail, but hopefully you guys remember some of this. You have a N-type, an NMOS transistor, and you have a PMOS transistor. Okay, this is sort of a little bit mangled by my iPad, but this says P minus, so that's acceptor dopants that are not so intense. This is N plus, this is N plus. So this is the source and drain of the NMOS. Here's the gate oxide. So here's where sort of the silicon surfaces. Okay, and here, this is the layers you've roughly grown on top of that silicon wafer. So here's the gate oxide, and here's the polysilicon for the gate of this NMOS. Okay, and here's the PMOS. The source and drains are P pluses. And because you're sitting on a P minus substrate, you're sitting in the same substrate that the NMOSFET sits in. But so you have to kind of create this well to separate yourself, if you're a PMOS, to separate yourself from the substrate. So you actually have to create this N well and then put your P plus source and drains, and then the gate oxide and the poly. So we're going to go through all these in detail. Or does this, anybody, I mean, I hope anybody not remember the NMOS, PMOS transistors? I'm hoping you guys all had this sort of background, but we're going to go into it in detail. But is it totally new to anybody? No? Good to hear. Okay. We're going to go through it in gory detail. Don't worry. Okay, so this is what's so-called a single well process, which means that you put this well down. Usually the well you put in for the PMOS transistors. Okay, alternatively, you could have a dual well process where you have a well for the NMOSFETs, whoops, and a well for the PMOSFETs. Okay, so again, what you see here is there's this substrate, P minus substrate. Here's designed in an epitaxial layer. Sometimes what people do is make the whole wafer. So this is the wafer, and it's going very deep, so it's a millimeter again. Sometimes people use P minus for the whole well, for the whole wafer all the way end to end. Or what they do is they build a P minus on the very top surface, and that's called a epitaxial process. Okay, and the advantage of that is you can get, well, I think we can talk about the advantage down the line, but usually epitaxial wafers have better performance in terms of some of the things that like latch up, substrate connection, some of those things. So they're considered to have better electrical performance, the epitaxial wafers, but they tend to be more expensive. So it depends on the product line you're running. You might probably do an epi process. So what happens then is you start implanting the sources and drains, growing the oxides, and then these. So again, the silicon ends. Let's say it sort of ends here. So to first order, anything that happens below this is happening with implantation. So what you're doing is you have the silicon material, you blast these things with donors, which are, what's a donor? It's typically like phosphorus. Or so that's to make N or N plus type material, or acceptors, which are typically, I think, boron or arsenic. And so these typically make P plus or P type material. So to get this sort of this N plus, I use this ion implanter. This wafer went into this piece of equipment that's maybe the size of, I don't know, a refrigerator, say, maybe a little bit bigger. And basically I have like a high electric field, and I shoot these ions into the silicon, and these ions create this N plus region. And depending on the energy that I shot the ions into this silicon, depending on the energy and depending on the concentration, it goes shallower in the material or deeper into the material. It's more of an N plus or an N, or a P plus or a P. So you have energy and you have the dosage, say, of implantation. So, but the upshot is anything below this rough line is stuff you're implanting into the silicon. Anything above this line is no longer didn't start being on the wafer. So here, anything above this, you're growing on the wafer. Like this gate oxide is a silicon dioxide that you grew on top of the silicon. This polysilicon gate, you deposited this polysilicon on top of the wafer, and then you shape it or pattern it, so-called. Or the silicon dioxide, which is, well, let's talk about this tungsten layer. Is used as this interconnection. You deposited tungsten to act to connect up your transistors together. So notice this piece of metal that I deposited on now connects the drain of the PMOS with the drain of the NMOS. So if I was going to draw the circuit of this thing, this PMOS would be this device here, this NMOS would be this device here, and this connection between them with this BP, this piece of metal. And because I want that piece of metal to be, I don't want it to short, I don't want to short this thing to the silicon, I need to have deposited this silicon dioxide dielectric, which is isolating that piece of metal. Okay, so anything above here, I'm depositing these interconnections, and I'm depositing the dielectrics between the connections. Okay. Okay. So what happens is, we're going to go over this a few times in detail, but generally what happens is you at the very high level, you do this kind of stuff. So the first thing you do is you define where the transistors are going to be, and those are so-called active layers, active areas. So this is where the transistors are. And for the purpose of this class, that's N MOSFETs and P MOSFETs. Okay, and then these trenches, you need to electrically isolate your transistors from each other. So these are isolation. So first you basically define where all your transistors are. So these will be millions, billions of transistors on your chip. They're all getting, like, all this is happening at the same time because you have a lithographic mask that's printing all the layers of your, sort of each layer of your transistor, of all the transistors of that particular flavor at the same time. But you're basically defining where all your transistors are going to be and how they're going to be isolated from each other. Okay. The next step is you create those wells. Okay. So the wells are, typically they're isolating PMOS transistors from the substrate. Okay, this step, you're depositing this polysilicon layer is typically your gate of NMOS and PMOS. Okay, then the next step is, so now these are just defining where the regions are. Next, you basically implant with this ion implanter, this sort of ion cannon, where the sources and drains are. So ion implanter. So this is actually creating N plus, P plus, N minus, whatever you're going to create. Okay. And then lastly, this is all happening in the silicon still, right? We haven't started going above it necessarily. But then lastly, we create contacts. So now you need to say you have your N plus. So at this point, you've defined this N plus, you've got your gate oxide, you have your poly. Now you need to, and let's say this is, you've got some oxide on top of the whole thing. I need to create a contact to this N plus. So you need to create an opening in your, you need to create an opening in your oxide and fill it with something that then can connect up to a piece of interconnection metal. Okay, so these are just the sort of the general steps. You're working your way from bottom to top. But again, this is just sort of at the very high level. We're going to go into the details. Okay, so when you're defining these regions, okay, you use a process called photolithography. Okay, so the way it works is you are, well, let's take it step by step here. So this is something that you keep repeating. So this is one cycle of something that you keep repeating in this process many, many times. So so the main thing that you create, one set of masks that get used for every wafer in your process. So that's kind of the, what's the word for it? That's kind of like your tooling you're creating. That's your casing that you're sort of, you're using that to create all the wafers. And it's this mask that what you do is, let's say you start at this point here, you put this material called photoresist, you spin that on your wafer, and you see this is kind of like putting a drop here and the wafer spinning. This photoresist material is something that's optically sensitive, and depending on what type of photoresist it is, it might get either more hard or softer if it's exposed to light. Okay, so some photoresists get softer or don't get any harder when they're exposed to light, and vice versa. And what you can do basically is, if you have this optical mask, so this mask is a piece of glass, with typically like chrome, probably misspelling chrome. Basically, it's got basically chrome shapes of what you want imprinted on the wafer. So this is your mask. Say you have a mask for your, let's say this is gate oxide for the sake of discussion. So you keep using the same mask for, let's say you're going to make 1,000 wafers or 10,000 wafers, use the same mask over and over again, okay? Then you have the particular wafer you're working on in your lithography equipment. And what you've done is you've deposited this photoresist all over this wafer, okay? Now use the mask to expose, now you shine typically UV light. Sorry, I'm using the same color for everything. Should shine UV light through this mask. Okay, and let's say this is a particular type of resist that where there are these chrome patches. These areas don't get any of this UV light, and the rest of the areas do. And so let's say it's a kind of photoresist where whatever gets the light gets softer, okay? So these regions get kind of harder, these regions here, and these greens stay sort of softer. So here's this point. So you've used your mask, which is this guy, and you've got your wafer with the photoresist on it. You've exposed it, and now you're left with this thing, okay? And then, sorry, you once you do the exposure, you got to develop the photoresist. That's usually go through the heating process, okay? So now it's made things that are exposed either harder or softer. Then you go through a process of etching, or that. Now what that process does is it gets rid of, we said this stuff is the soft part, so it gets rid of the stuff that was soft, okay? This acid etch, it gets rid of all that stuff. And then you do another prep process on that, okay? And now you do the whatever you were gonna do. Let's say we said this would be a gate oxide deposition, okay? So now this is this process step. So now you want to deposit the gate oxide. So you deposit your gate oxide, and it gets deposited wherever there's no photoresist. Okay, so these would all end up being gates. Okay, and then the next step is you remove the photoresist. So you remove this carefully. So you end up with this gate oxide in these areas. Okay, and then you go through the process again many times until you get your CMOS part. Now, a typical process has something like, because you got to think about, if you're looking at this, this cross section, there's a lot of layers, there's a lot of patterns here. If you think about, if you did this step by step by step by step, each step you define a region, and in each step you may do an implant or not, or deposit or not. It's a bunch of steps. So typically you'll end up with something like 30 to say 60 masks. Okay, so depending on your process. So these are actual physical masks. It's like pieces of glass. And these are very precision made parts. So these are pieces of glass with chrome defining the regions where you'd like the transistors, et cetera, to be. Okay, and then this process, depending on, again, the process, because some of these masks are, by the way, are expensive. So remember we talked about, I don't know, we talked about let's say, let's talk about a 40 nanometer process. So the mask set for that might be about $1 million. So to create these masks, once you design your chip, you've got a database for these different masks. And then to build a mask is going to cost you about $1 million, say, for a 40 nanometer process. That dollar amount goes up sort of exponentially as you get smaller and smaller. So say a 28 nanometer process, maybe those masks are going to cost you, I don't know, like 5 million, something like that. And so on and so forth. And then because these masks are expensive, what people try to do is to use the masks for more than one step. Let's say use the mask plus, use 2 different types of photoresist. So you use the mask and then use the negative on the mask and so on. Or with some masks, there might be multiple steps. So the number of steps in a process is typically, like 100 plus of these cycles happen with these 30 to 60 masks. Okay. And usually it's, the foundry, the schedule for this is roughly, usually it's 1 to, say, 3 to 6 days per mask. And these are calendar days, not business days. That means like a week is, so if they tell you it's 6 days per mask, like about a week goes by, and then you have, let's say if you're in a 30 mask process, you have, you got to wait 30 weeks, which is like, more than 6 months to get your wafers in the foundry. And those are the kind of schedules you've faced with. So typically from the time when you give your database to the foundry, so from database, they call it, when you give your database to the foundry, this is called tape out. Because back in the day, you really put this on a magnetic tape and send it out, but the board stuck. So from there to getting your wafers, takes somewhere between 12 and 26 weeks typically. So say 3 months to as much as 6 months. And that schedule, and so this is like a significant amount of time, okay? It's a very, very long time. No, and think about that, you might have spent 6 to 12 months designing this database. You're designing the chip. That might take you 6 to 9 months to design the chip. Then it's going to take another 3 to 6 months to make the chip. So from the time you start your design till you get your first, engineering samples, which is your first samples. Some people call it engineering samples. Some people call it alpha samples, it might be easily like a year to 14 to 18 months before you see your first samples of a part. So it's, a very long time. And then think about that you've spent during this time, you've already spent your $100 million plus or whatever, depending on the process of design. So this was your NRE. Remember, we talked about that. And you still don't know if your design works or not. You still, after you spend $100 million is when you get that chip back to start testing. Of course, that depends on the process, depending on what you're doing. Okay, so a very long time. Okay, Furthermore, let's say you're in production. When you're in production, what happens is you still end up with this 12 to 26 week cycle. Let me get it, see if I can get it answered. Whoops. So you went through, spent 6 to 9 months for the design, maybe longer. It depends on what you're designing, right? So let's say this cost you, I don't know, by the time you paid for your CAD tools and your expensive engineers, all that stuff, maybe this cost you like, I don't know, if you're doing an expensive design, 100 million. Okay, and 6 to 9 months, and then let's say the fab takes you 3 to 4 months to get the part fabbed. So here you've spent, you've paid for your masks. Let's say they were expensive masks. It was a tight process, so it's 20 million for, I don't know, 14 nanometer process. Okay, so now here is when you have your engineering samples. And all this dollar amount is non-recurring engineering expenses. Okay. Now let's say you. So when you're designing, looking at a product, okay, this is one of the things you look at. You look at, okay, how long is it going to take me to design this chip, and how much is it going to cost me? Is it worthwhile for me to design this product? And is the market still going to be there in a year and a half when the chip is out? Okay, so that's the main things you worry about there. Relatively straightforward. Okay, now let's say your chip worked or whatever, or you modified it, whatever. Now you've got a working chip. Okay, so now you get a purchase order from your customer. You got the chip, you sold it to your customer. Okay, so the first thing you do when you get your chip, it's called, you get a socket. So you win the socket. Your marketing and sales guys have been working with the customer this whole time, and the parts come back, and the customer says, okay, you get the business. That's called winning the socket. So let's say you're a vendor for Apple. Apple is going to come up with, I don't know, iPhone 14, and in 2-3 years you start your design now. In a year and a half, the whole time you're talking to Apple about what they want, and sometime in 2011, 2012, you get the first parts, you start characterizing it, you give it to Apple, like these engineering samples, they plug it in, they go, okay, it works like we want it, and okay, you're telling us you're going to sell it to us for, I don't know, $10 a piece or something in millions, whatever the deal is you're getting with Apple. And so, okay, so you won the socket at that point. That means that you're going to start being able to sell parts to your customer. Now you've got your cart tied to the horse of your customer. If they have a successful product, you're going to be able to sell them a lot of parts. If they don't, all this NRE is going to go to waste, essentially, or you won't recover all of your NRE. Okay, so anyway, you won the socket. Now your customer, Apple, starts shipping cell phones, and now they're going to start giving you purchase orders. Okay, so what they tell you is, here's a piece of paper that says, if you ship me, you name it, if you ship me 100,000 parts between now and So let's say in the next, So give me 100,000 parts, and if you give me 100,000 parts at $10 a piece, then I agree to pay you. Okay. And so what happens is there, in a purchase order from your customer, there is a volume, defined, like how many parts they're going to buy. There'll be a price, and there'll be a payment terms. It'll say, okay, I will pay you 30 days after receipt of these parts, or 60 days after receipts. By the way, I'm going off on, I think it's an important segue, but it's a bit of a segue about sort of what actually happens in the business part of this fabrication. Hopefully that's interesting for you guys. Okay, so that's what the purchase order says from the customer. You then, so this is from your customer, then you give a purchase order to the foundry, and you tell the foundry, you've said, okay, I'm going to have 1,000 parts per wafer that are yielded, so I'm going to need 100 wafers. So you give a purchase order to the foundry, and you tell them, if you send me 100 wafers at I don't know, $3,000 a piece, I'm going to pay you 30 days after I receive those wafers. Okay. So now the foundry, once it's got this purchase order from you, assuming you have good credit, they're going to start making so this is PO from customer to you. And like a day later, you send a PO from you to Fab. Okay, then they start working. And then 3 months later, they ship you these 100 wafers. So you have 30 days to pay them. So you have to pay them month 4. Month 4, you owe the foundry $300,000. Okay. Now, let's say though, you got these parts. Now you got to test them, you got to package them, you got to test them, you got to ship them to the customer. Let's say that took you 2 months, do all that good stuff. And let's say now the customer has it, and now they have 30 days to pay you. Okay, so that means you have a cash flow issue here, because you had to come up with this $300,000, say 2 to 3 months before you get paid by the customer to recover that $300,000 plus make a profit. And this is a cycle that's sort of constantly repeating. Okay, so you're constantly getting purchase orders from the customer and giving POs to the foundry, and you have to pay your vendors before you get paid from your customer. So when you hear in the news that such and such technical, it doesn't have to be technical company, such and such company has, or maybe you hear from people who own businesses or whatever, has a cash flow problem, it means that it's taking them too long to get paid by their customers, given their expenses, that they have to put up too much upfront cash, and they're like running out of that upfront cash. So a lot of companies actually go bankrupt right here because they, it's possible you've got a good product, you've got a great customer that's increasing their volume very quickly. You need a significant amount of dollars. I use this example, so it's only $300,000, but it may end up, could easily be like $30 million when you need to basically have this 10, 20, 35 million dollars to float before you get paid, or else nobody's going to do anything for you, and you just go belly up, although you have a good product and you have a good customer. So anyway, that was a segue about the scheduling for this process, and the quicker this fab process turns around, the faster you get paid and the less of a cash flow problem you have. So in manufacturing, the faster you can manufacture something and the faster you can get paid, the better it is. Okay. So sorry about that segue, but it's like an important part of, when we're looking at building something, it's going to cost you a lot of money to build something, and you're going to have to get paid to build it. But you have to, a big part of it, just besides doing the technical work and managing the vendors, is managing the finances and managing getting paid from the customer and paying your vendor. It's like could turn into a really bad situation or a good situation depending on how good those vendors are, how much money you have, how good your credit is. All those things start being just as important as having a good product. Okay, so segue on sales. Now back to the foundry process. So again, now we're going to talk about sort of a visual of what we talked about. Is, say, in this case, well, actually, let me just jump straight to here. So now we're going to go through step by step the process. Okay, so a little hard to see here, but you start from, this is your wafer that's whatever, a millimeter thick, and then this is a particularly epi process, meaning that you have this P minus, P epi is P minus layer, and this is usually 5 to 10 microns thick. Okay, so the first thing you want to do is create, I think this is starting to create the isolation. So the first thing you do is you grow silicon nitride, which is a layer also used for masking. Okay, and before the silicon nitride, you've grown a silicon dioxide layer. Then you mask the silicon dioxide. So what you do here, say you used your mask and you deposited, say, photoresist everywhere, and you use the mask to get rid of the photoresist in these areas. So we got rid of the photoresist here and here and here. So there's no photoresist there. And then you do, say, in this particular case, you do a plasma etch, which is a type of just getting rid of the material. So where there's no photoresist, you cut out this chunk of the material. Okay, so you get left with this this is nitride, silicon dioxide. Okay, so then what you do is you grow and you get rid of this, where you don't have the nitride, okay, you grow another thick layer of oxide, and that serves as your isolation. So these are acting as isolation, And anywhere these things aren't, this is your, shoot, sorry guys, this is, so it's like, these areas are so-called active areas. So any place where you don't have this thick silicon dioxide, that's isolation between your transistors, all these areas are where your transistors will go or connections to the transistors will go. Okay, so-called active areas. Give me such a thick line. Anyway, so the next thing you do is you want to define your well. Okay, so let's say you want to put your PMOSFETs here. Okay, so you mask this everywhere else other than where you have your PMOSFETs, and you implant. For a PMOSFET, you need an N well. So this should be an N well. So you implant donors here, and you get this N well here. Okay, and then you also want to adjust the. So you have your N well. This is a dual well process, so you want to also put in a well for your N MOSFETs. So this should be a P where the N MOSFETs are. So now you mask everything else other than where your N MOSFETs are, and you implant your acceptors there, so you end up with P-type material. Okay, so the next step is you put in your polysilicon gates. By the way, before then, you've also deposited your gate oxide. See, it's a very thin oxide. Okay, so this is also an oxide, but this is a very thick oxide that's used as isolation. This thick oxide's quote unquote thick. Let's say that is, I don't know, like 0.1 to 0.3 microns thick. Okay, this oxide here, this light blue here might be like, I don't know, like, I think it's that, maybe like 300 angstroms or something thick. Okay, because you need a very thin oxide for your gate oxide for it to be effective. Okay, so then you deposit your polysilicon gates on top of that. And this is like a CMOS process. It's called every time you put one of these layers down, it's like any other manufacturing process. There's these uncertainties about, like, is this like going to be here or is it going to be a little bit over? So there's like this slack that you have that things can move with respect to each other. The one thing you absolutely cannot have, so let's say I'm going to draw for you guys a NMOS transistor. So let's say I'm going to make, so this is the oxide, this is the poly. So let's say I want to make a contact to this N plus. The contact could be here, or it could be a little bit over, so there could be some uncertainty in where the contact is in this N plus. It doesn't matter very much, okay? And a lot of the layers are like that. Like, things are overlapping other things on purpose because with manufacturing uncertainty, a little bit of movement here and there, you'll still be okay, and you want to do that. The one place that can't be any uncertainty is this N plus for your source or drain. has to line up exactly with the poly gate. Okay, if you have a situation where you have like things moved like that, so there's a gap here and this is not going to act like a transistor, okay, because this gate can no longer influence the electric field here, meaning that your transistor is going to be an open. Okay, so there absolutely cannot be, it has to be exactly aligned. So what they came up with this is a process that's called a self-aligned process. And by that they mean, what they mean is they're using the polysilicon itself as the mask for the source drain implant. So what they do is they put down the polysilicon and they implant your N plus around there. And so you end up N plus all the way to the edge of your poly, but as soon as the poly is there, it blocks the N plus from getting into the channel, and then it picks up again where there's no poly, and you have this self-alignment between the poly gate and the source and drain. So this is what this thing is doing, is it's, you first deposit the poly and then you implant and you end up with the P plus or N plus exactly where you need it on either side of that poly. Okay, so now at this point here, at this point here, now you've got all your transistors created on your substrate. Okay, you have all your N MOSFETs, you have all your P MOSFETs, and then you have the isolation in between. Okay, now it's time to start connecting these transistors together. So now you get into a process of depositing. So this is where this was, everything was happening more or less in the silicon except the poly deposition, but everything was in the silicon. Now, starting at this step here, everything is going to be happening above the silicon. And now everything's happening in a deposition. So you deposit a silicon dioxide layer that's going to act as a insulator or dielectric. You open it up, and then you're gonna, next step is you would deposit, say you want to hook up this N MOSFET source drain. So this is the N to the P source, to this, the N MOSFET drain to the P MOSFET drain. You open this thing up and you deposit some metal aluminum, say here. So this silicon dioxide doesn't let your aluminum short down to the silicon. It's your ice, it's your ice insulation. But these openings in the silicon dioxide are important because you want to reach down to the N plus layers, to the drains. Okay, so here is the aluminum that you deposited, so, and pattern. So in this case, you have, this is the source of your PMOS. This is the source of your NMOS. And this is the drain of NMOS and drain of PMOS shorted together. Okay, so this circuit will look like you've got your PMOS FET, you got your NMOS FET, whoops. Got your NMOS FET. This here is this point, this connection between them. And then you've also created a connection to the source of this PMOS that you're going to do something with, and the source of this NMOS that you're going to do something with. Okay, and then because you've got a lot of, let's say you have 1 million, billion, whatever transistors on your substrate, and a lot of these need to be connected to, all of them are connected to other transistors. So what you want to do, is have a lot of these different metal layers. So it's insulator, metal layer, insulator, metal layer, insulator, metal layer. And then they're sort of so this is, say, the first metal layer. Let's call that metal 1. Then you deposit, so I'm looking at it from the top down. Okay, from the side, it looks like this. Let's say this is metal 1. Then I deposit some oxide everywhere. So I deposit oxide, so I'm looking at it at cross section. Okay, then I put my second layer metal. Now, because I'm looking at a cross section now, because there's a silicon dioxide dielectric between this metal 1 and metal 2, they don't short together. So I can run lines across each other and not get a short. Okay, so now you're going to go to your third metal layer, right? So now I'm going to sort of do it slightly offset. So this is my third metal layer. And so I have another layer of oxide, and then this ends up being my metal 3. Okay, so basically, because there's this layers of silicon dioxide and conductors, I can get, very complex routing between transistors. And, a very advanced process might have 7, 8 layers of metal. More simple, it's hard to see a process that has less than 3 or 4 metal layers. Okay. So after all this is said, anyway, now at this point, you've got all your metal layers. There might be many, many metal layers here, but they've only shown 1. And then lastly, put a last metal layer to put your wire bonds, and we'll talk about what those wire bonds are, et cetera, to connect to the silicon chip. And if you do, if you look at a sort of a 3-dimensional drawing of a transistor, it kind of looks like this. You have this is an NMOS transistor, and you have your substrate, you have your source and drain. So we were looking at it kind of from this direction, okay? You had your polysilicon gate, and you had the thin ox for the gate. You had the metal connections. You had this oxide. That was the thick oxide. That was the insulation. Okay, so that's kind of like defining your transistor. So now looking at this from how do we create all these masks? Okay, the way you do it is if you look at this again from the top down. Okay, let's say this is what we drew. So here is, let's say, a top-down view. This is going to be what you create in the CAD tool, say. Yeah. So here is a NMOS FET. Here is a PMOS FET, looking from the top down. This is the NWEL. This is the active, this is N plus for source drain. So I guess you can look at the cross section here, right? So here we have the N plus for the source drain of the NMOS, N plus for the source, N plus for the drain. This is the polysilicon gate for the NMOS. This is the polysilicon gate for the PMOS. Plus, they've made it a little bit longer because they're probably going to use this polysilicon gate for to connect to something else. Okay, and then this is the P plus for the PMOS drain, P plus for the PMOS source. And this is gonna be the N plus for the contact to the well. And this is the P plus for contact to the substrate. So you can see how things are like lined up here, the cross sections. Okay. So that's what you want to draw to give to the foundry. So you want to draw this, you're drawing this top view. You're dropping down a bunch of rectangles in your CAD tool, and each one of them is going to be drawn in its own layer. So when you go in deposit, when you go in your CAD tool to draw these things, you draw the end well as a rectangle. And then you change your layer type, and you draw the active as a bunch of rectangles. So this was the same as this guy here. Okay, these actives are the same as this, this, and this, this, and this. Okay, then you draw your poly. And then, so this poly is here, and this guy is here. Okay, and you draw, then you do the contacts and so on. So what happens is each one of these things turns into its own mask. Okay, this ends up being the end-well mask, etc. But when you submit this to the foundry, this will have a layer number. So layer number 4 that you agreed with the foundry, that this will be the layer number for the end-well, this will be the layer number for the P, so on, or active, and so on and so forth. Okay, so this is what you'll actually be creating in your CAD tool. Okay, this top view and these drawings. Okay, and when the foundry overlaps all these, you get your transistors. Okay, and the way you draw these things is with a set of rules that are called design rules. And so what, for the foundry to be able to make sense of these drawings, they are telling you, for example, don't make this thing thinner than a certain size. Don't make these things closer than a certain size. Make these an exactly a certain size so that the foundry, can use this mask to make something usable, because they have their own process variations, they have their own lithography limitations. So these are a set of rules that set the minimum widths of certain lines, spaces between certain lines, and so on for each layer that makes this thing producible. Okay, so let's stop here, guys, and then next lecture I'm going to talk about specifics of what these, like a typical set of rules, looks like. Any questions?
Professor?
Yeah.
Where can I find the syllabus and the class schedule for this class?
It should be on the Blackboard.
We can't access it. At least I can't.
Has anybody else been able to access it?
I haven't been able to access the syllabus either.
Oh, no? Anybody been able to access it?
Yeah. I was able to get it. I can access it. But they go in course information, and it says syllabus template, but that's the actual syllabus. Like if you click on it, it's actually the document.
And it should like download.
Yeah, it's kind of a weird.
It downloads as all file. Yeah, it says I cannot open it.
If you have Word, you can like right click and then try to open with Word. That works.
You can also open as HTML file, and then it should open fine.
Or you could just rename the file.
Okay, I see it.
docx. That works too. if you're on Windows 10.
I found it.
Guys, how can I access to video lecture?
I've been, unfortunately, the last video lecture for some reason didn't get recorded. Sorry about that. But I am recording the lecture. I put them on YouTube and then putting a link. So there should be a link, I think, for, let's say this is lecture 3, I think. So lecture 1, a link to it should be on the Blackboard.
Okay, thank you.
Sure, and if you click on it, it'll get you to the YouTube video.
Thanks.
Sure. Any other questions, guys? Okay, guys, take care. I'll talk to you guys on Thursday.
Hi, thank you, Professor.
Thanks.
Thank you. See you
Thank you,
Thursday.
Professor.
Thank you.
Thanks.